Hey Arch, what's going on? Today, and actually the rest of this week, I'm studying AASHTO. Just getting refamiliarized, since now I won't be able to bring this with my tabs. Need to make sure that I understand the layout. How about you? What are you up to? Yep, studying for the lateral portion of the SE exam. Working on a structural design problem. Very cool. What are you up to? Or I should say, what's the problem? And then I'll let you get back to it. Very cool. I like it. Stupid question, is the Boston Company building located in Boston? You've been here since the beginning. Love it. I love it. Yeah, it's a vertical case truss structure. Ooh, wait. So like the lateral system is K-braces? If it is, yikes. At least, well, Boston that works because it's a non-seismic region, but K-braces, no bueno, no bueno. Not permitted for a lot of buildings nowadays. Hey, Justin, welcome in. No, well, yes, the SE exam splits from taking a bridge exam versus a building exam, but that's only for the afternoon portion of the exam. The morning portion of the exam is combined, and both bridge engineers and building engineers have to take the same morning portion of the exam, which contain building problems and bridge problems. It clears some stuff for the big AASHTO book. It takes both lateral and gravity loads. I think I read that the Boston building is one of the lightest skyscrapers ever made. Really? Interesting. I'd have to look that up, I'm not sure. I do know that wasn't there a famous case in Boston, I think it was the John Hancock building, but I could be wrong, where the natural frequency of the building wasn't, or was aligning with the wind loading criteria of Boston, so it was what do you want to call it, like resonating or accelerating, and then like a bunch of the glass windows were blowing out, so they had to put a large chunk of mass at the top of the building. Is that John Hancock building? Or I don't know what they call it anymore, but I thought that was that one. If it's possible, would you be able to show me how you would go about getting a force on the diagonal of the K-truss with a wind and gravity load acting on the truss? I would love to do that. I can't do it right now, though. I got a week until my exam, and I gotta study AASHTO. Yeah, unfortunately, I can't right now. I would love to, but I cannot. I'm a bit lost because I could do it, but it's a lot more than a back of the envelope problem. I mean, you can keep it simple. Get your story force at each story, and then just rudimentarily draw your K-brace, and then, you know, you got your big building here, and you got all your floors. And then you got your, I don't know if your K-brace is doing that, or if it's doing, well, oh no. Oh lordy. Huh. Is it doing this? Like, is that really what you're, that's what it looks like? Or is it just a braced frame, only it's like not a chevron, like doing something like this? That would be a lot better. Sheldon, a strong team member. What's going on, my man? Look at that green badge, I love that. It's been a while, come to study? Hell yeah, man, come on in. Front row, we got your popcorn ready, your usual drink, I love it. Ivan, welcome all the way from Cambodia. Hey, I love you popping in here, that's awesome. Can't think of myself taking the SE exam. You're a Texas PE, and I can't get the additional motivation to study after work. Good for you. I got motivated when I heard it was changing to computer-based, so that was, whatever, a year and a half ago. And just tried my hand at it, and then when I got into studying, I was like, you know what, I can do this, and I'm learning a lot, so that's what, the gained knowledge is what is continuing to push me forward to get through this thing. Now that I'm halfway through it, and I thought I was all the way through it, but unfortunately didn't pass lateral, here I am, kind of almost there, so I want to finish this off. Where'd I get my undergraduate degree from? I got it from the University of Massachusetts, Amherst. I got both my bachelor's and master's there. It's a V-shaped truss. Oh, so you mean like a chevron? You got a chevron going on? Hoo. You got, tell me you got this going on. Is that true? Is it number 1 versus number 2? The anticipation is killing me. I'm guessing the V's are upside down. Really? They have an inverse chevron. Okay. I mean, same thing, kind of different, slightly different forces. got it right the first time. Okay, I was like, I haven't come across an inverse chevron before. All right, there we go. There we go. All right, let's get these out of them. Let's get this one out of the way. So for the future, something when you're talking with your colleagues, this is something that, here, let's get this. Something that I learned as as I'm studying right now for steel, for the lateral exam, the difference in terminology, different types of braces. So this over here is called a chevron. And then you have just a normal braced frame is when you have just a single brace coming across. No specific name to that. This, although you might see, like, you know, if I draw it in green, you might say like, oh, I see a K right here, so it's a K brace. That is not correct. What a K brace is classified as is like you have a building and your K brace is doing that. So the brace doesn't have a beam at the intermediate point, which is horrendously bad for a lateral system because what's happening, and they're not permitted in a lot of applications, because what happens is you have this concentrated force that's point load from your brace reactions that are pushing on your column, which will cause your column to buckle, and it's just, you never want to be putting lateral point loads on your column system. The columns are supposed to be the strongest thing possible in your system, minus the actual brace itself. Usually for steel design, it's capacity design based on the capacity of the brace, and you design everything around that. But yeah, K braces, no bueno, especially in seismic country. This is a chevron, and we're rolling. So what you want to, how do you know if you need a single brace or a double brace for lateral support? It doesn't matter. You can choose either and design both systems are applicable. You just have to design for the forces based on the geometry that you choose. For the chevron condition here, Arch, what happens is, I'm guessing, so you're in Boston, since it's not seismic, I am assuming that they're just, it's a concentric brace. So this is a concentric brace. This is an eccentric braced frame. Do you have concentric as number one? My pen has like stopped working. Or do you have eccentric number two? Because those are two different lateral systems as well. Eccentric frames are, you're concentric. Okay, beautiful, beautiful. Eccentric frames are more difficult in my opinion. Wow, my pen is really struggling. I've noticed that the past couple of days. Good. So you have a concentric frame, and they're not BRBs or anything. Like it's just a steel brace frame. I would assume for Boston. And so like this is a wide flange, and this is a wide flange, or it's an HSS. They're just steel members. They're not like steel members wrapped in concrete or anything like that. So what you need to make sure of is to design your beam. You'll have gravity load on your beam, and then you'll also be designing that beam for a reaction from your brace, both an up and down reaction depending on what's going on here. But it'll be an unbalanced case, which is if force is pushing this way due to wind, this brace will go into tension. So it'll be stretched apart, whereas this brace will be pushed into compression. And we know that steel is good in both tension and compression, but it's significantly better in tension. So tension, you get to you have to make sure you're calculating the reaction, because if this man, I am like all over the place. If the portion of your beam that is in tension means that it's going to be pulling on your beam, whereas the compression member is going to be pushing back up on your beam. So the compression component is pushing up and the tension component is pushing down. You might say, well, if they're the same size brace, then it's an equal and opposite force. So the summation of these two is equal to 0. Well, that's not true, because your worst condition is the full tensile capacity. I'll just do phi Tn of your brace in tension will be significantly larger than your compressive capacity of your other brace, because we know that when we push in compression, you have a buckling effect depending on your effective length and all that kind of stuff. And what you'll find is that that value is lower than your tension capacity. So the summation of these will be unbalanced because your T will be significantly bigger than your C. Now, the code also mandates that you have to, I don't know if this is just seismic application or all application, but you need to design this chevron brace for a post-buckling condition of your compression member. That means that you have to design for the full capacity of your tension member, and then you need to design for 30% of your, I'm just going to do phi Cn, even though that's not how you draw that. 30% of your compressive capacity. You might say, why are you designing for less capacity? Isn't that under conservative? What that does is that makes your compressive force even smaller than your tension force. So the unbalanced total resultant force will be even larger. So there will be a larger point load on this beam. So you design your beam for that point load as well as your distributed gravity load over the beam of the concentric brace. And there you go. Then you're off to the races. Similarly, when you go down, now we're, now we're going down. You got your wind. You have tension pulling up, which means it's pulling your column, but that's being resisted by this beam down here. So you have a tension or compression force in this beam below, and then you have a compressive force here, which means you have a compressive resultant, a tension component pulling on the beam. So you have double effects happening. And you take those unbalanced loads again, and you start designing for that as well. So that's kind of a super, super rough idea of how you start doing back of the napkin design of a concentric brace frame. All right, I gotta get back to AASHTO. No problem. And that was just the tip of the iceberg, and I was probably all over the place. But that's the beginning part. And it's funny because I only know how to design these based on the steel seismic manual, because everything out here is seismic design. So I have this, which tells you how you need to design those things. I'm guessing just from a wind perspective that you have in Boston, I don't really know how to. I'm guessing you just use the normal steel manual, you get your forces, and you just start designing your members. Yeah, California, it's all seismic controlled. All right, I'm gonna get back into it. I love the interaction in the chat. This is great. Everyone, get in your seats, talk amongst yourselves. I gotta knock out a couple of problems here to stay on track. I got one more week. Let's get after it. Hey, Jeremiah Kim, welcome to Team Kestava. Grab your seat in the auditorium. Hey, welcome in, everybody. From Chicago, welcome in. Kai, hello, hello. Khan, welcome in. Hey, Stephen, welcome in. Unfortunately, I'm locked in with some AASHTO. We got a little bit longer here. I can't believe we're already close to an hour. So I gotta focus on AASHTO for the next week. But then I can get into that again. So unfortunately, you're out of luck today, but I appreciate you stopping in. Chef Tony, welcome in. You know how it is. We're getting close to the end here, so we gotta keep on keeping on it. Shit. I have to remember to not use my tabs when freaking going through AASHTO. I don't have an electronic version like I don't think anybody does. Oh, Daniel. Whew, coming in hot like that. Okay. You know the email. Oh, that's all I'm saying. Head to my channel. You'll find the business email there. I get you, Daniel. You are committed. Studying a little AASHTO for your PE. Man, I'm proud of you. Never even cracked this thing when I was studying for my PE.
do I move in this world? Could you please tell me what the hell I'm doing for it? Bring me to my knees. I'm so stupid, would you tell me honestly if I wasn't meant to be what I see when I dream? Where do I move in this world? Could you please tell me what the hell I'm doing for it? Bring me to my knees. I'm so stupid, would you tell me honestly if I wasn't meant to be what I see when I dream? It's a big, big world out there. Plenty possibilities. All of them is killing me soft. I want the real me figured out right here, right now. Is this lifestyle the right style for me? Only with time will I see. But by then it'll be too late. Looking in the mirror at a stranger's face. If I wasn't right, would you tell me straight? Or would you let me? Where do I move in this world? Could you please tell me what the hell I'm doing for it? Bring me to my knees. I'm so stupid, would you tell me honestly if I wasn't meant to be what I see when I dream? Where do I move in this world? Could you please tell me what the hell I'm doing for it? Bring me to my knees. I'm so stupid, would you tell me honestly if I wasn't meant to be what I see when I dream? I want something great instead of all dismay, but I can't find my way. I fall on my face, I flatline my faith. I want all escape, let's throw it all away. Just like the thoughts I trade for a couple of bucks in this big bucket of love. I'm steady throwing my up, hoping for that 1 in 100. But fuck stressing the numbers, pop this deck in your summer and see the inner of my head declog like a plunge. Y'all be akin to my feces, your best bet be the Bee Gees. The way you think living's staying alive. I got my head and my smile, but don't know where I'll fly. I'm just spreading my wings, I'm fine with taking my time. I used to rush it all out, I'm trying to slow it all down. Take my feet and lose ground, give them somewhere to hang. I always want it right now, trying to slow it all down. Take my mind and lose ground, watch it floating away. Yeah. Where do I move in this world? Could you please tell me what the hell I'm doing for it? Bring me to my knees. I'm so stupid, would you tell me honestly if I wasn't meant to be what I see when I dream? Where do I move in this world? Could you please tell me what the hell I'm doing for it? Bring me to my knees. I'm so stupid, would you tell me honestly if I wasn't meant to be what I see when I dream?
It is raining so hard outside right now. Hang on, I gotta go see this. I can't get over how hard it's raining here. I gotta go see one more time. Like, everything's gotta be flooded. Quick break. I'm gonna knock out a couple more problems and then I gotta get off too. It's getting a little bit later. We'll be right back. All right. We're back. Get back in your seats. Oh, Jesus. There we go.
Oh, I'm gone, my friend. Won't you tell me the answers again? My heart bleeds red, but there's no point in telling me why. No point in telling me why. Oh, can't seem to challenge any thought that leaves my mind. Guess my receiver damage is all I hear are thoughts like mine. Oh, I can't help it. I'm just selfish to the core. Upon self-reflection, think I should mention that I'm better than you are. Oh, I'm so vain. I wrote this little song, it's about me. I'm so vain. Oh, I'm so vain. I wrote this little song, it's about me. I'm so vain.
This is shout out to the man inside the vanity mirror. Love growing gradually, my plan to self-directed is clear. Used to be I'd rather be with anybody else but the mirror. Seeking validation, thinking it's the end of that era. Hope my honesty scare you, cause I be scaring myself. Looking deep in my reflection like you pretty as hell. Here's some more about myself, I got a story to tell. And for the sake of my bank account, hope that it sell.
Oh, I can't help it. I'm just selfish to the core. Yeah, on self-reflection, think I should mention that I'm better than you. Oh, I'm
I'm gonna fucking smash my monitor in a second if this pen doesn't start working. And I think that's gonna be the cue to wrap it up tonight. I just need to finish this problem. The struggle bus over here is real though with this pen at the moment. All of a sudden, just the past like couple of days, it's started to die, and I just put a fresh battery in. I don't know. Unfortunate, but it's not. Might have to look into getting something else. I don't know. All right, everybody. I think we're gonna do it tonight. It's getting a little late. My pen's on the fritz. So that's annoying. I gotta figure that out. But we're moving through some AASHTO. We're moving through wind. Moving through stream loading right now. About to be done with that. Then I'm gonna move on to I don't even know what next. Some earthquake stuff, some seismic stuff. Yeah. So it'll be good. It'll be good. And yeah, I got like 40 problems to get through in this great. I highly suggest everybody get it. Everyone who's left in the auditorium, that is. This guy by David Connor, shout out. This is a really great tool for all you non-bridge engineers out there who are studying. It just gives a wide variety of more problems that prepare you for the SE exam. So get your hands on it. It's nice. It was really nice to have it as a reference document in the paper-based format, but now that I can't do that, it's more so a tool, more problems to help you understand how to move through the AASHTO code and be familiar with it. So that's the name of the game now with this type of computer-based testing. All right, everybody. Had some ups and downs in this study session, but it was a little one. We were here and we were getting the job done. I will see you all probably tomorrow because I'm going to be doing some every single day this week to get through in time for the exam next week. Good luck, everybody. I'll see you next time. Have a great evening, morning, anything in between. And that's about it. Like the video, like the stream. You don't have to if you don't want to, though. All right. See you.